We're going to get started. It's my great pleasure to welcome you to the 10th Annual Food and Sustainability Day Fair. This is our second day. How many of you have already been to at least one teach-in? How many of you have been to at least two? Okay, well, you still have opportunities to go to more. My name is Alex Carr. I'm a professor of geography in the Department of Earth, Environment, and Physics. I just want to make a couple of brief announcements about what's happening today and in the next couple of weeks around environmental issues and food issues. And then I will turn over to my distinguished colleague, Professor Dunn, who's going to give you an introduction to climate. So at all of your tables, there should be at least one of these information sheets. There is all kinds of exciting things happening today. Today we're really focusing a lot on food, but obviously climate and the environment as well. There are food films screening just around the corner all day. There will be a mobile vendor market today around lunchtime. There are a number of amazing vendors right outside the store. I will remind you at the end to go talk to them. There's beekeepers, there's green and efficient technology you can check out. There's eventually Ask a Climate Scientist. There's departments represented. There's the library. There's all sorts of exciting people to talk to. Later today, let me make sure I get the time right. From 1:30 to 3, there's a make and take to make your own cleaning products. So if you want to get some cleaning products that aren't toxic, we're going to help you guys actually make them. So that'll be upstairs between 1:30 and 3. So there's, check out the schedule. There's a bunch of exciting stuff happening today. There's also obviously more teach-ins that you might be interested in. And then coming up, so if some of this stuff catches your attention, next Monday, the 23rd at 6 p.m. In the Blue Lounge, so right next door in this building, we're screening El Rio, which is a documentary about the Amazon River, which is amazing. So if you're interested in those kind of issues, please come check that out. And then on Thursday, the 26th, we are participating in a national screening of an Inconvenient Sequel, which is Al Gore's new film about climate change. So a bunch of the stuff that we're going to talk about today, the film is really focusing on what we're doing about climate change. So that's going to be a pretty exciting opportunity. It's not really being screened anywhere else yet. We're going to be one of a few hundred college campuses. Before, there will be a live webcast with Al Gore and John Kerry, and talking about the film and what's happening. And then former Vice President Al Gore is going to answer questions from students. Lister State is submitting a question. We'll see if he takes it. And then coming up in November, there'll be more environmental film nights, so keep an eye out for posters for all of those events. So Monday, Thursday, and then again in November, there'll be more films and events happening on campus. So with that, thank you all for being here, whether your faculty brought you or not. We're glad you're here. And I am very pleased to turn over to Dr. Dunn, who's going to talk about climate.
So welcome everyone to Climate 101. And before I get started, I'd like to gauge whether or not I need to use the microphone. So for those of you in back, can you hear me now, or is it better? Oh. So it's good? Okay. If you've been in one of my classes, you know I kind of like to pace back and forth. So that's how I'm most comfortable. So welcome to Climate 101. I see some familiar faces. I see some new faces. This is all great. And a little bit about what we're going to be talking about here in Climate 101. First, let's get our language straight. Let's talk about what's weather. Let's talk about what's climate, and think about how they relate to one another and how they're different. And then we're going to look at some of the recent patterns in Earth's climate. You're going to look at some data from NASA. That's what those little packets on your table are. So don't open them until I tell you it's time. And then we'll think about what's controlling Earth's climate. What are the important factors out there and how they might be changing? And lastly, we're going to look at some predictions. That's what we all, are concerned about, the future. What does the future look like? What are the different possibilities? And what can we do to have an influence on our future? And so, I have this roadmap, but there's lots of room for your questions and your input. It's a big, complicated issue. And so if there's something up here that's confusing or you've got a question about, raise your hand. Let's stop and pause and make sure we're all on the same page. So, first, let's just talk about some vocabulary. So, when I say weather, what am I talking about? What's the weather today? What's it like out there? Cold? Cool? So yeah, maybe you're sensing that fall coolness in the air. Maybe you noticed it was sunny. Maybe a light breeze. So those immediate observations, that's what weather is. Weather tells us the current state of the atmosphere. And so it can encompass a lot of different variables. The temperature, cool, warm, in between. Precipitation, is it raining? Is it cloudy? What's the atmospheric pressure? So weather is, in an instant, what's happening right now. Climate is a little bit different, but it comes out of weather. What climate is, it tells us the average weather for a location. So usually climate scientists will take all these, say, daily temperature averages for 30 years, put them together, and take the average to figure out the climate for a location. So the climate isn't just based on today's weather, it's based on today's weather and the other 29 years of weather that preceded it. So climate, it comes out of weather, but it comes out of a lot of weather data, and that's really the difference here. And so my college professors always told me that climate is what you expect, and weather is what you get. You know, if you think back to your knowledge of what October climate is typically like, you might be expecting some frosts in the morning, needing to wear a hoodie every single day. But if you're preparing to go out in the morning, you actually look at the weather to figure out if you need that hoodie or not. So now that you've learned a little bit about the difference between climate and weather, think about the past few weeks. You know, we're about 3 weeks into October now. How do you think the weather of this October compares to what the climate for October usually is? Colder, warmer, wetter, drier? Any thoughts? I hear a few warmers out there. So yeah.
I think it's more variable.
So you think there's also been some variability? Yeah. And you know, variability is something we often see at this time of year, but we have had some ups and downs. If you think about Monday morning, we had a frost, and then you know, yesterday you could be out in a t-shirt. So luckily those nice folks at National Weather Service have put together what October has been like up till now, and I can bring this to you guys. So this is looking at the average temperature for October, all the Octobers in their data set. So here we are, Worcester 2017. The average temperature, so taking all the night times and daytimes, has been 59.1 degrees for 2017, up until the 17th. So that's the fourth warmest October on record. So for all of you who said warmer, you know, you're on the right track. And I don't have variability statistics, but that's something we could certainly look at too. So it's true for Worcester, it's true for Boston. They also looked at Providence and Hartford, all across New England. We've had a warmer October than average. And you know, you just with your experience living around here, you can sense that. And most weather forecasts suggest that as the month goes on, this number 4 might creep up towards 2 or 1 because it's forecast to continue to stay warm. So we're seeing that the weather of Worcester this October is warmer than the long-term climate. So now let's sort of think a little more globally. And at the beginning of this year, there were a whole bunch of headlines that came out. You might have seen some of them. 2016, the warmest year since records began. U.S. scientists officially declared 2016 the hottest year on record. That's 3 years in a row. Out of curiosity, who saw a headline along those lines this year? Anyone? Maybe it came across your news feed. This made a big splash. It was back in January, so maybe it's fallen off our radars too. But this was a big news story that we've got information saying that 2016 globally was warmer than average. And so here we're going to take a look at how Earth's temperature has evolved through time. And so we're going to look at what the data are actually showing for 2016 and the years before, so we can get a sense for Earth's climate and if Earth's climate has shifted. So what you're going to be doing is you're going to look at some data. This comes from NASA, and you'll see the web page when you open up your packets. But first I want to just make sure we're all on the same page about this graph. So this is a graph showing us the year, so starting in 1880, going through 2016. You might wonder what's special about 1880. Our thermometers got to be much more accurate. That's why we start to use our temperature data around then. We don't really trust thermometers from before then. And then this is not just temperature. It says temperature anomaly. You can see the numbers are either a little less than 0 or a little positive from 0. So it's a little different than how you might normally think of reading a temperature graph. Does anyone have any idea what an anomaly means? For people in GS 101, you've had some experience looking at this. Something's anomalous. Is it average or is it different? Different. So an anomaly tells us how different a temperature is from the long-term average. So what you're going to do is look at different years of data and interpret what is happening with temperature. So we're going to be looking at this temperature anomaly data. It's all relative to a 30-year climate average. It's from the middle of the 20th century. So when you are looking at the data, when you see a negative number, that tells you it's colder than average, and a positive number is warmer than average. So now, open up that packet 1 on your table. There should be a few pieces of paper in it with this graph. They're all the same. And there's some guiding questions. I'd like you to look at it and chat about it with your table. We'll take 3 to 5 minutes to look at it, and then we'll reconvene. For folks in the back, I've got some at the end. So you guys on this end, look underneath your. Awesome.
What does it
All the different lines represent just a year's average amount.
one line.
It's true. Well, there's 2, but there's one that goes like down. It's like
I wonder why that was spiking.
Let's take a few minutes to chat about what we see. I hear a lot of interesting observations across the room, and I'd like to hear some of those brought forward to the larger group. Okay, so we've been looking at this graph of what year it is and what the temperature anomaly is, and I heard some discussions about what different groups were seeing in the graph, what sort of patterns. Would anyone like to share what sort of patterns they saw? And there's a lot. There's no one right answer. Is it staying steady? Yeah, what did you guys notice? We saw an increase over time to higher values, but it's not quite that. There's also some complexity too. What did you see?
It kind of fluctuates, so like in 1910 it starts to decrease, but then you can also see it increase right after that. So
Yeah.
I think it's just going down and up. But we also said after 2020 that it was going to keep increasing.
Right.
That was our idea.
So you notice there's sort of decadal, maybe 10 or 20 year fluctuations. Sometimes it's going down, sometimes it's going up,
Yeah.
and then you
I mean,
start looking
obviously
to
there
the
were-
future. Maybe it'll go up quite a bit. Any other points that people saw that were interesting? Yeah.
Yeah, I also saw the trend from 1940
Mm-hmm.
to 2000. The temperature increased by half, and that's like about 60 years. And from 2000 to 2020, the production is gonna go half within that 20 years instead of 60.
Yeah, so you made an interesting observation about the sort of rate of change we're seeing here. You see one rate of change from this time period of about a half a degree. It took 60 years here, and then you point out it only takes 20 years to go up that much here. So the pattern isn't staying the same through time. That's maybe what your observations are suggesting. What you guys are doing is you are using the same climate data that scientists at NASA used when they were trying to figure out what's happening with Earth's climate and is it shifting. Yeah, so there's a lot of fluctuations, and this is one of the things that makes looking at climate and climate change so tricky, because we know weather can be variable. You can get a cold year. You can get these blips downward. You really have to put it all together. Yeah.
Then would the decline in the 1900s, that World War I,
So right, it's timed around World War I.
and then the peak in 1940 is that World War II?
So I think most models suggest that it wasn't driven by the wars per se, though the industrial activity associated with wartime industry might have had an effect. So I think I heard a couple groups noticing it going kind of down in this period, the post-war period, and that some suggestions, some scientific analyses have suggested that this is due to a process called global dimming, that industrial capacity ramped up during the war, and then, continued to ramp up in the post-war period. There weren't many pollution controls. And so if you've ever seen a picture recently of China and its air pollution problem, maybe you've gotten a flavor of this, so that sunlight can't reach the ground when there's too much pollution. And so there's some thoughts that part of the low temperature here was due to industrial activities like that. But it's really hard to pinpoint. It's tempting to tie it to one human event, but it's usually a combination of events in addition to these human effects. Yeah, good questions. So, okay, we have limited data, clearly, but let's think about the future. Let's think about the year 2100. Any thoughts what it's going to do? Yeah, what do you think?
Well, just looking at, maybe it was like 2015 on, I had a steady increase, and it seems that the annual mean is closer to the 5-year mean. So if temperatures are predicted to go up, maybe the annual mean and the 5-year mean won't deviate as far as past has shown.
So you're noticing that the 5-year mean is lined up really well with the data.
Yeah.
And so, yeah, you might expect, if this pattern continues, you could see that continuing on into the future. So, less variability around the mean. So maybe that would happen. Yeah, and then that would indicate an upward trend. But, you've all observed that there's this increasing trend, but of course, we don't have enough information to think about what's going to happen 80 years from now. All we can say is that the trend looks like it's going up, and that it looks like it's increasing, like you observed. So, partway through today, we'll start to look at some different predictions of how temperature might change by then. But these are all great observations you've made. Did anyone have any questions, or is there anything unclear about this data you looked at? So before we go on, I just want to draw your attention to the fact that this data is all paid for with our tax dollars. It's available at that website right there, climate.nasa.gov. And so, I know there can be a lot of misinformation out there regarding climate change. This is why the data is so powerful. You just looked at the data and you made your conclusions based on the data. No one filtered it for you, which is pretty amazing that we can just grab data like this. All right, so this is the same data portrayed in a slightly different way. This is from NOAA, the National Oceanic and Atmospheric Administration, looking at the temperature anomaly again since 1880. Every year in red was warmer than the whole 20th century average temperature. So I'm looking at all these faces who are younger than me, and I'm thinking that your entire lives have been spent in years that are warmer than average. And so this is showing us that it's not just like one year's weather, it's actually a shift in climate, because climate's usually based on 30-year or longer averages. The last 30 years, those are much higher than the middle of the 20th century. So already we have evidence of climate changing. Those averages are shifting. So what could have just been 1 year of weather has been repeated year after year, and now it's actually playing into the long-term climate. And someone over there commented about how the trend seems to be changing. And so that ties in nicely with this. Here again is the entire temperature record that you look at. This is a nice smooth version. So 1880 up to now. If you take the whole data set, you see that temperature is increasing, just like you observed. But if you look at the last 20 years, this yellow is probably hard to see for you guys. It's going like that. It's got a steeper trend. So one, we see a trend to warmer temperatures, and two, it seems to be accelerating. And so this is why we have reason for concern. We're going to look at some of the different dimensions of this problem over the course of this hour. But before I do that, I want to introduce a really important organization that you should know about. It can look kind of like alphabet soup when you see it in the media. It's called the Intergovernmental Panel on Climate Change, or the Ipcc. This was established by the United Nations all the way back in 1988 when they were coming up with their framework convention on climate change. And so it's not a research organization, it's an organization of scientists that gets together to figure out what is the risk of climate change, what are our vulnerabilities, what is happening out there. And what they do is they don't actually perform the science. They go out and they evaluate all the science that's out there. And so they don't just look at one scientist's paper about how mice are responding to a warmer climate in Worcester. They look at all the researchers' investigating how different plants and animals are responding. And to give you a sense of the work they do, their last report was released a few years ago. I'll be showing you a lot of info from the physical science part of their work. There are 800 authors. There are over 2,000 pages in the last report, just Working Group 1. And it was based on more than 9,000 peer-reviewed scientific articles. So I'm going to try to show you mostly stuff from the Ipcc simply because it has the weight of this much science behind it. And you know, I also want to encourage you to access this. If you ever need to do a report on climate change for a class, all these reports are available here at ipcc.ch in giant PDF form. And if you ever have questions about it, you can come and see me or some of the other faculty in Earth, Environment, and Physics. We are always happy to help people understand this. All right, so in the last IPCC report, they made this statement. And it's measured and clear, but it shows the danger. Warming of the climate system is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed. The amounts of snow and ice have diminished, and sea level has risen. So they're basing this on data like the data you just saw, of changes in temperature, and also indications of change in other parts of Earth's sphere. So let's figure out what's going on, what the physical basis is for this change, and what some of the factors are controlling Earth's climate. And that way we can start to think about how it might change in the future. And I think it's useful to start at the beginning. What is the source of energy for life on Earth? I hear lots of whispered suns. Yeah, not a trick question, you're right on. The solar energy is the basis for life on Earth. You and I, everything depends on that solar energy coming in and being photosynthesized at the base of the food chain. Sorry?
Geothermal.
Geothermal's there, but it's so much smaller. But you're right, it's there and it's, you know, fractional percent. There's always a more complicated answer. Okay, so here's the majority of our energy source, barring that geothermal energy. So here's the sun. The sun sends solar energy to us and it warms the surface of the Earth. It sends solar energy to us and plants photosynthesize. And if you took GS 101 with me, you know there are a bunch of gory equations you can go through to figure out the temperature of the Earth based on the sun. Based on the sun's energy, you should get an average temperature of the Earth of minus 18 Celsius. And I saw a couple of eyebrows go up, 0 degrees Fahrenheit. That's cold, right? When it's that cold in Worcester, we complain. And Worcester is one of the colder parts of the world. And if you look at the actual temperature, you find that Earth is much warmer, about 15 Celsius, 59 Fahrenheit. That sounds a little more reasonable based on our experience with this planet. So something's going on. The sun only gives us enough energy to make us this temperature, but instead we're a much more pleasant temperature that supports life on Earth. And the way it goes is like this. We know the sun sends solar radiation to the Earth. The Earth's surface and atmosphere absorbs this energy and it warms up. What is invisible to us but equally as important is that the Earth actually sends energy back out towards space. It's in infrared wavelengths, so we don't see it. But if you've ever walked across an asphalt parking lot in the summer, you might kind of feel the heat emanating from it. That's that heat coming from the Earth. That happens everywhere. There's just more of it when it's hot out. Okay, so the sun sends energy to us. The Earth releases energy to space. But not all of it makes it there. Some of this heat is absorbed in the atmosphere by gases. We call them greenhouse gases. Greenhouse gases are things like carbon dioxide, CO2, water vapor, H2O, methane. And what these gases do is they capture that energy, they absorb it, and they re-radiate it back to the surface. So this makes the Earth warmer. I like to kind of describe it as the heat is being recycled. Heat that was going to escape is recycled back to Earth, and that makes our temperature much warmer and much more habitable for life as we know it. So when you hear the term the greenhouse effect, that's what this is talking about. And it's a normal part of Earth functioning. Without the greenhouse effect, our planet would be really different. But Where things get complicated is when the levels of greenhouse gases in the atmosphere start to change. So now what I'd like you to do is open up packet 2. What you're going to look at is the amount of one of the greenhouse gases in the atmosphere since 1720. Take a look at this, chat about it. Let's talk about this CO2 data, and then we'll talk about how we can use this information to think about the future. So, first off, let's look at this, and so we've got a data set from 1740 onward telling us about the amount of one of these greenhouse gases in the atmosphere. And did anyone catch how these measurements were being made and how that changed through time? Was someone out there in the Revolutionary War measuring CO2? Among other things? Yeah. Sorry? Oh, thank you very much. We thank you for the data, Dr. Dillip. How can you figure out how much CO2 was in the air back then? I know we talked about it with some of the groups.
Revolutionary War, how did they figure out CO2?
Yeah, I saw a hand up back there. Yeah.
They took parts of the ice and polar ice caps, and they were able to read they have technology now where they can read how much CO2 is in the layers of the ice.
Perfect. Yeah. So this is really important. You know, when you see scientists report something from the Revolutionary War, they didn't just pull it out of thin air. They developed a technique like that student described to actually look at ice cores from polar ice caps like in Antarctica or in Greenland and look at the air inside those. If you've ever looked at an ice cube, you may have noticed there's tiny little bubbles of air. They analyzed the air in those tiny bubbles. And that's why maybe there's fewer points than you would expect, because each data point was really painstaking to access. So this is how we know about the past. And it was only in 1958 that we started to get data measured actively in the atmosphere right now. The scientist named Keeling had the great idea to put a sensor on the top of Mauna Loa in Hawaii, and he made a whole career out of studying CO2 in Hawaii, which sounds like an excellent career choice. And he's produced this data set that is one of the most fundamental data sets to atmospheric science. Okay, so we've got CO2 concentration either from ice cores or from being measured actually in the atmosphere currently. And so, what did you notice about the patterns here? And maybe the patterns here related to the first figure. What's going on? What did you see?
They kind of correlate, both with the variabilities at the beginning and how it kind of evens out at the end.
Yeah, so you notice that there's, especially at the end, there seems to be a correlation. You see a big leap up in CO2, and if you think back to that figure 1, that's corresponding with the time when temperatures are rising. And whereas in the earlier part of the data set, you maybe don't see such a clear pattern. Yeah, so something's making CO2 go up. Any thoughts? What's putting the CO2 in the air? Humans. Oh, sorry, there's someone else.
Combustion?
Sorry?
Combustion?
Yeah, combustion. So, you know, I think many of us have started to do combustion in our houses as the temperature's gotten colder. Maybe you turned on your furnace, maybe you use oil, maybe you use natural gas. We take it for granted, but that process of combustion that she describes turns gas or oil into CO2 and some other byproducts. And so humans, and specifically humans combusting fossil fuels, is where that CO2 is coming from. So this is showing from the Global Carbon Project analysis. This is 1958 when we started making CO2 measurements in Hawaii. And this is the amount of CO2 going in the atmosphere from us. And you can see burning oil adds it, burning coal, burning gas, all of these add CO2 to the atmosphere. So it's human actions. And you can actually study the isotopic signatures of this CO2 and directly trace it to fossil fuels. So there's no dispute that this CO2 in the atmosphere is due to us. We are responsible for the increase. Okay. So let's put those two graphs together. You know, many of you noticed that there seems to be a correspondence or correlation between them. It doesn't go that far back. It only goes to 1880 in terms of temperature. but we see this intriguing connection between temperature rise and CO2 rise. And there are scientists who've gone further back in the past. So to look at how CO2 and temperature vary. This is looking from the year 1000 to now. And so I know there's a lot on here, but this is showing you the amount of CO2. It was relatively low and steady until recently. It turns out, if you go to those ice cores and you look at those bubbles, you can go back 800,000 years, and CO2 was never as high as it is now. And so CO2 has gone up, and this red line is a temperature construction, and that's gone up. So we see a really strong correlation. And I know many of you here are chemistry majors and have had statistics. Correlation does not imply what? Causation. Thank you. So we see this connection, but that's not enough to say, okay, well, CO2's fault, let's get on with it. We need to have more evidence to tie this increase in CO2 to that increase in temperature. And the way that scientists do this is through the use of climate models. So climate models are similar to the weather models, which forecast weather, 5 days in the future. You might think, well, geez, weather models are terrible 1 week in advance. How can we expect to forecast 100 years in the future? The thing is, climate models don't try to predict when we're going to get a nor'easter in 2050, which is a good thing. All they're trying to do is predict what our average climate will be like in 2050. And we think they're pretty good at that. So let me show you some evidence from climate models to help us understand what's causing the temperature increase. So here we have 2 different climate models that were used to reconstruct recent climate. So by recent climate, I mean 1979 to 2005. You might wonder, why do that, right? Those years already happened. We already know what happened with temperature. But the idea behind this is that we ran one set of climate models that used all the natural factors, but none of the human factors that affect climate. So like sunlight, how strong is the sun, ocean circulation, volcanic eruptions. This model used all those natural factors and then added in the CO2 increase from us. So that is the only difference between these models. This one has our CO2, our methane, etc. And what this did is it gave them a test, because they compared the models with what really happened. That's what really happened. You can see that some areas had a temperature increase that was pretty high, other areas had a smaller temperature increase. And now you can compare what happened with the models. The first thing you probably notice is none of these match exactly, right? Models are not perfect. But I think probably most of you can agree that this color pattern matches this better than the top model matches this. What this is for scientists is this is evidence that the warming that has already happened, the warming that you observed in your data, that has to be due to the human emissions. Because the human emissions alone can produce that pattern. So in the media, they don't go into the details usually. They'll just say, scientists say that warming is due to humans. But there's actually a lot of scientific evidence to back it up. And this is what led the Ipcc to make this statement as well in their most recent report. It is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century, i.e. that big warming trend you noticed in the second half of your data. Continued emissions of greenhouse gases will cause further warming and changes in all components of the climate system. Limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. So now we're pivoting from what has already happened to thinking about the future. We know it's warming. We have a high degree of certainty that it's due to us. Let's think about what it means for the future. So before we start to look at the future, are there any questions up to this point? Yeah.
In one of the charts, the temperature was less exponential. There was less exponential growth than the amount of CO2 that was in the atmosphere.
Are you thinking about this one?
Yeah, the first, the one before.
You know what has to do with the time frame you're looking at. So this guy, you're looking only at 1880 to 2020, whereas this one, you're going back to the year 1000. So there are so many ways graphs can be displayed in different ways that can make it confusing. So yeah, it's good to ask questions about this. So here's our 1880. We were just looking at this part of the cycle. So it looks different because the scale that we were looking at in the previous one is now compressed.
I was looking at the previous two, the temperature and then, if you look at from 1880 on both charts, the rise in
1880 is
CO2.
So you're wondering why this one looks more like that than the temperature?
Right.
So here's where, I was annoyed. I could not get the data from Scripps in exactly the same time. So this starts at 1720, and this starts at 1880. So in other words, if I lined them up, they might look a little more similar. Also, it's not a one-to-one relationship between the two. You know, the direction is the same, but it's not like one is going to influence the other in a linear way. Yeah. Any other questions about this? All right, so let's think about the future. So, you know, everyone wants to know about what's going to happen with climate. And we can use these same climate models that we used to look at the past to think about the future. But here's where things get a little tricky. We know climate depends on CO2, but we don't know what CO2 in the atmosphere is going to be like 50 years from now. How are we all going to get to our jobs in 50 years? Are we going to take magneto-levitation trains? Are we going to have plug-in cars? Or are we going to use, you know, cars that are getting 10 miles per gallon? We don't know that. We don't know what our transportation infrastructure will be like. We don't know how we're going to heat our houses. So we don't know what CO2 in the future is going to be. So what scientists do is try to imagine a couple of different pathways. They call them representative concentration pathways, which is a mouthful. I'm sorry about that. RCPs. You could just think of them as different sort of storylines, different, you know, pathways humanity might choose to follow in the future. And what they're going to have is different energy use patterns and different amounts of climate warming. Let me explain. So I'm going to just show you a couple of these different scenarios. If we continue doing what we've been doing, we will continue to grow our emissions of CO2 in the atmosphere. That's what this red line is showing. So if our emissions continue to go up, the CO2 in the atmosphere will continue to go up. So by the end of by 2100, we'll have over 900 parts per million of CO2 in the atmosphere. On the other hand, if we make choices to decarbonize our economy, switch away from gas, oil, and coal, in the next few years, we might follow this path. If we follow this path, the CO2 in 2100 is going to be really different. It's a little over 400 parts per million. This is a big difference. So which way we follow is going to determine what our warming is going to be. And just to give you some context, we're right around here. We are really at a decision point about where our future is going to go. And each of these pathways translates into a different amount of climate warming. So now we're going to look at the actual temperature change predicted. So I'm switching to data from the US's National Climate Assessment, so now we're in degrees Fahrenheit, which might be a little more familiar to you. And so what we've got here are the predictions on our current path, so if we continue to increase our emissions. And these are our emissions if we rapidly decrease our use of fossil fuels. That's a huge range, right? We might have warming of a little bit over 2 degrees Fahrenheit or over 8 degrees Fahrenheit. And here's where the media does the public no favors. What you'll often see if you read an article about climate change in the media is they'll say, scientists say it will warm between 2 and 8 degrees Fahrenheit. And they don't explain why it's such a big range. So the general public reads that and they think, geez, the scientists have no clue. I'll wait till they have a clue before changing my lifestyle. But the reason why you have this big range is because we just don't know what choices we're going to make in terms of energy use. And at the end of today, we'll talk about some different pathways for reducing energy, fossil energy use. So this is kind of our possible future. It's somewhere in there. And, you know, I get it if we look at those numbers and think it doesn't sound like that big a deal. You know, the temperature, I watched my car's temperature as I drive to Worcester in the morning, and it shows me the outdoor temperature going up, you know, 6 degrees, 8 degrees just during my commute. I kind of belong to it. So that, an average warming of that might sound really small because we get much bigger daily fluctuations. But the thing is, the way it plays out over the course of the year actually is a big impact. So I'm going to show you a couple of New England specific projections. This is from the Northeast Climate Impact Assessment, and that's all available online. So it matters which pathway we choose. If we choose to do nothing, if we continue to follow the path we're on, by the middle of the century, our climate will be like Washington, D.C.'s. By the end of the century, our climate will be like, I think it's around Myrtle Beach, which, is probably very pleasant in the springtime, but I think as New Englanders, we might find it a tad hot in the summer. In contrast, if we reduce our emissions, we end up with a climate that's more similar to what we've historically been used to, more like the mid-Atlantic states. Our climate by the end of the century might just be like Delaware, where a lot of the same species that live now could probably still survive. Whereas a climate like South Carolina would have a whole different set of plant and animal species that could thrive. Put another way, heat waves. So in New England, most of us don't have central air conditioning. I know I haul up some big window units every year. I know a lot of us are stuck doing that. And New England is predicted to get a lot more days where you want air conditioning. So historically, and I'm sorry I don't have this data for Worcester, the impact assessment only did it for Boston and Hartford. So Boston has typically had 10 days above 90 Fahrenheit. At the end of the century, what it's going to be depends on our choices. It could be more than 60 days above 90 degrees if we continue doing what we're doing. Or if we cut back that number in half to about 30 days above 90 degrees. So it's not a question of if we're going to warm, it's a question of how much, and how much can we live with, and how much can society support. Okay. And, we could spend an entire semester looking at the impacts. We see that there's probably going to be changes in crop yields. We see there's going to be change in water availability. There's a lot of different parts of Earth's spheres that are expected to experience changes. I'm going to skim over this one because I want to look at sea level rise, because that's one that's often featured in the media. Maybe you've heard a lot about it. So as climate warms, the oceans get warmer. They actually take up more space. And ice caps melt. You get more water in the oceans. So the sea level has already risen almost a foot since we started taking records. It's going to rise more. How much more? We are not sure. It depends on how stable Antarctica is. It depends on how stable Greenland is and the rest of the mountain glaciers. So all we can be sure of is that sea level is going to go up. And so this is something that is not an issue just for the future. It's an issue for now. So actually, if I go back here, you can see that currently sea level is already higher than it was when a lot of our coastal cities were developed. So already a lot of our coastal infrastructure is being impacted by rising sea levels. So what we're going to watch is a little, if I can load it up, YouTube clip. This is from St. Petersburg, Florida. It was just a couple weeks ago, October 7th. Every year it has, in the autumn and spring, some times of especially high tides. They're called king tides. Maybe you've heard that term. And so these are when you notice the effect of rising sea level. So we're going to watch some video of how these people experience high sea level. Notice that it's sunny. There's no storm. There's no hurricane. This is flooding just due to high tides at a time of sea level rise.
You didn't make it to the beach today, well, chances are it might have made it to you. That is, if you live anywhere near the coast. Gulf waters creeped into the streets of St. Pete Beach, in some areas reaching as high as 4 feet deep. Our Andrea Lyon was out during the high points today and explains what's happening to protect homes.
We're out here at Casablanca Avenue on St. Pete Beach. Just a few hours ago, the water was as high as my knee at this point. Right here, it's dry, but behind me, that's not the case. Water's still a couple feet high out there. And believe it or not, this is due to something called king tide from the harvest moon.
I just can't believe this.
Those heading to enjoy warm, hot Gulf water didn't have to go very far this morning.
I went running, and when I came back, I couldn't even get home.
Janice says she was gone for just an hour. And the water came up another 3 inches.
This is the first time it's been this high in years.
Her side of the street, not as bad as a block down.
High tide and the streets are flooded.
Where Philip Spano even offered to take some laps in that clear floodwater.
No gators or anything.
We turned him down, but did find one of his neighbors is actually the public works director for St. Pete Beach.
Well, you live on a beach. It's an island paradise, but it has repercussions.
Mike Clark waited from his home to talk to us.
There's nothing wrong with the stormwater system.
Pointing out the key indicator that this is Mother Nature's fault is the water on the street is the same level as the water in the bayou.
It's been like this before, and it's not a hurricane right now. At least not here.
No rain or another hurricane is not responsible. It's actually the harvest moon.
I was just asking somebody if it's a full moon.
Which causes king tide to ebb and flow.
Okay, so that's it.
It's expected to last a few more days.
That's wild.
Crazy.
The water out here is expected to be at its highest Sunday through Monday. After that, it should recede pretty quickly. The public works director tells me that this site, Casablanca Avenue, along with 24 others, will be improved over the next several years, meaning when this happens again, the only way water will be on this street is if it comes over that wall. On St. Pete Beach, Andrea Lyon, ABC Action News.
So clearly it was an astronomically high tide, but if sea level hadn't risen, the water wouldn't have been able to come up into those neighborhoods. And so this is happening across, especially South Florida. It happens here too, not in Worcester, but in Boston. So if you've ever been to the New England Aquarium, maybe you went on a school field trip there once, that's Long Wharf underwater during the May king tides. So king tides are when we notice the effects of sea level rise. It's risen overall, but the king tides are when it really starts to intrude on our infrastructure. So this isn't something to think about just for the future. It's happening now. And it's costing a lot of money as people have to sort of rebuild their infrastructure. Miami Beach is spending hundreds of millions of dollars to try to shore up its infrastructure. And so this is an area for concern, especially for the coastal parts of Massachusetts. So this is a map that was put out by UMass Boston in collaboration with some other agencies, trying to look at the vulnerability of parts of Boston under higher sea level. So it's a little bit tricky to read this. What this is showing is what will be underwater at the mean high tide plus 7.5 feet. So 7.5 feet sounds like a lot, but Hurricane Sandy, that rose, had a storm surge of 14 feet in New York. It arrived at Boston at low tide, so Boston was lucky. So any amount of sea level rise makes these areas more vulnerable because it means you need a smaller storm to cause flooding. And if you're wondering what the kaleidoscopic colors are, the oranges are where you'd expect kind of a shallow flood depth, 0 to 2 feet. The magenta is 4 to 6 feet, and kind of the deeper orange is more than that. So if you look at this, and if you've been to Boston before, that's a lot of expensive real estate. Like if you've been to Newbury Street, Comm Ave, that's all there. That land wasn't there 200 years ago. We infilled that. We made that land. The New England Aquarium, Faneuil Hall. I think the Faneuil Hall Marketplace you can kind of make out by those little lines right there if you've ever been there. That whole South Boston waterfront that they're building up. This is all vulnerable. And you can look at it and say, well, phew, glad I live in Central Mass. And, undoubtedly less immediate danger here in Central Mass, but you don't think that all our taxes are going to have to help take care of this problem? Here's MIT. MIT is not going to let itself flood. There will probably be a rebuild of the Charles River Dam, and that comes out of, all of our pocketbooks. We preserve the infrastructure we need. We build dams to protect places. So this is going to affect all of us, even if we're not directly on the coastline. And I'm going to skip this one and get to sort of the global big picture. Because Boston's a small city, relatively speaking. But globally, if we think about the megacities of the world, so megacity is a term meaning a city with 10 million or more people. Every dot here is a megacity. And every red dot is a megacity that's inside a low elevation coastal zone, meaning that it's vulnerable to sea level rise. And so if you look at this, almost all of the megacities of the world are located in places that are vulnerable to flooding. And so this means tens of millions of people will be affected, first with high king tides and when storms come through, but maybe later in the century by just everyday high tide. There's going to have to be a big reckoning in terms of infrastructure. And so the other thing to see, I know there's a lot on here, is the colors. If you see the darkest green color, that shows the percentage of the population who's in these low elevation zones, vulnerable to flooding. And you can see some countries with huge populations have most of their population within those low elevation zones. So, you know, it's a problem close to home, but it's a global problem as well. And so rise in sea level is really going to be felt across the world in the coming century. And this isn't the only challenge these low elevation coastal zones are having. There's rising sea level, so it's coming from the ocean, but there's also changes in storm patterns. And I realize this has been kind of a crazy autumn in terms of natural disasters, hurricanes, wildfires, and whatnot. But way back at the beginning of the semester, you know, end of August, beginning of September, there was one city that got completely nailed with rain. Does anyone remember that? Got 5 feet of rain. So there have been too many disasters, clearly. We can't remember them all. So Hurricane Harvey, you may have heard about that right before classes started. Hurricane Harvey came up through the Gulf of Mexico and danced around Houston for multiple days. So we're going to watch a visualization from NASA of the rainfall. Okay, so this is a rainfall satellite. So Harvey's going to come up from the Gulf. Here it is. So those colors are the rain. And it just danced around. It got sandwiched between some weather systems and it couldn't get out of there. Went back over the ocean. Okay. So probably some of you heard about it when it was happening. It's just been now superseded by Irma and Maria and the wildfires and all this crazy stuff that's happened since September. So move away from the dancing blobs and look at what happened total. This is showing the amount of rainfall they got. So this actually wasn't the final data, but this is the best visualization I can see. This is a huge area that got multiple feet of rainfall. And so with the final data, they actually found that there were several parts of Texas that got over 60 inches of rain in less than a week. 5 feet of rainfall. So more than they typically get in a year. And so scientists have been racking their brains trying to visualize how much water that is. It's over 33 trillion gallons. Put another way, that could fill the Chesapeake Bay in the Mid-Atlantic 2 times. It's just an unreal amount of water. So, you know, maybe you didn't see this particular graphic. Did anyone see any pictures of the flooding that was happening? There were some pretty scary pictures. So downtown Houston was completely devastated. This isn't sea level rise, though. This is an intense rainstorm. So, you know, it can be tempting to say, well, you get an intense rainstorm every once in a while. That happens anywhere. Turns out, though, that this was Houston's 3rd 500-year flood in 3 years. So to earth scientists, we say a 500-year flood is a flood that happens on average once every 500 years. So somehow Houston has had 3 of them in 3 years. So mathematically, it's possible. You know, each year you have a 0.02 probability of it happening, but 0.02% probability. But clearly, this is wildly unlikely to happen in the absence of climate change. So here's the way the connection goes between climate change and extreme rain. If it's warmer out, you can have more evaporation. You maybe have noticed your puddles disappear faster in summer than winter. So you get more evaporation, that means you have more moisture in the atmosphere. You have more moisture in the atmosphere, you can make more rainfall. And so the thinking goes that the more climate warms, the more capacity we have for extreme events like this. And if you look at what's happened up till now, this is showing what has already happened. So the observed change in very heavy precipitation. You can see that everywhere in the country except Hawaii for some reason has had an increase in big precipitation events. like Houston saw. So you can't necessarily blame any one flood on climate change. You can't point to this and say, well, that's climate change, that one there. But what climate change really is doing is it's kind of loading the dice. It's making these types of events happen more frequently. It's making, hurricanes when they happen more potent. So it's really kind of amping up the system and making things more extreme than they used to be. And so we've seen this already in terms of past precipitation. And this is something we think we're going to see in the future as well. So how much? That depends on us. If we keep on doing what we're doing, this is that RCP 8.5 scenario, we expect a significant increase in heavy precipitation, especially in the Northeast, incidentally. So, 3 or 4 times as many events. If we cut back, we're expecting a smaller increase in these events. It'll still happen, but not as much. So again, our choices are going to help determine our future in this way. So, we could keep talking about the future effects, or, till the cows come home. I have a class in that, by the way, contemporary climate change, if you're interested in this. But I want to kind of talk about, in my last slide, policy. And so the international community has already agreed, with words at least, though not necessarily with actions, that these outcomes are bad. We would like to keep our climate warming to about 2 degrees Celsius. If we want to keep our warming to 2 degrees Celsius, that means this is the maximum amount of carbon dioxide we can emit. You can think of it as our budget. And once we spend it down, we go over that threshold. We go into overdraft. Okay, so this is our budget. We've already spent most of it. So this is showing the different ways we've spent our carbon budget. Greenhouse gases that aren't CO2. This is our fossil fuel use. This is deforestation. Those all add greenhouse gases to the atmosphere. This is all we have left. If we use more fossil fuels and emit more than this, we're going to exceed our threshold, and we're going to start to see some of the really negative effects of climate change. So we only have about 22% of our budget left for the future. So clearly, we need to get off this pathway. This is that pathway towards extreme warming, and these numbers are in Celsius, not Fahrenheit. We need to get off this pathway and down to one of these pathways if we want to stay in that temperature range. So how do we do it? It can feel pretty discouraging from an individual perspective, but I do want to mention some ways that we can have an influence. And the most important is voting and putting pressure on politicians. If it's important to you that climate be stable in the future to you, and not just because of having to pay tax dollars for infrastructure, but because it promotes global stability, vote for politicians who share your views. And you can make choices in your own life as well to shift more towards green sources. Both National Grid and Eversource have options to buy renewable like energies, like hydro, like wind. You can see that at massenergy.org. You can, if you've got a really old oil furnace, switching to natural gas will result in less CO2 being emitted. Mass Save has some info on that. And, transportation. Worcester's doing a great job trying to get more transportation options to campus. We've got the bus, we've got the bike share, and there's a lot more fuel-efficient and hybrid cars out there. So, clearly as college students, you may not be in the market for a new car now, but think about it when you are after graduation. And lastly, efficiency. Efficiency is like unsexy. People don't like to talk about it, but it's the low-hanging fruit. The easiest energy to save is the one you never use in the first place. Turning off lights, only using cars when you need it, etc. So I wanted to stop here and allow some time for questions. We've got a couple of minutes, I think. Also, I'll be at the Ask a Climate Scientist group from 1 p.m. onward. So thank you for coming, and any questions?
Yes.
Okay, I was looking at that clock and I